Hello guys, welcome to another video. Today we'll be treating the topic structural mechanics and we're going to be analyzing the reactions of a rigid frame. Stay tuned. Thank you. Okay, so this is analysis of rigid frame. So this is the frame. We have a pin support and we have a roller support. So you might be wondering how do we approach this load that is on top. We have a UVL, uniformly varying load. We have a UDL, and we have another UVL on this side. And they said the total unit weight is 26 kilonewton per meter. So there are two ways to go about this. Now, if you look at this shape, this is the shape of a trapezium. When we had a triangle, right? When we had a triangle, we used 1/2 base times height. When we had a UDL, this is a UVL, by the way. When we had a UDL, load like this, you remember we use length times breadth. Now that we have a trapezium, area of a trapezium is equal to 1/2 open bracket a plus b close bracket height, right? We can treat it that way. We can take everything as a trapezium. And when we took, if it is a triangle, to get the distance, you look for the centroid of the triangle. That's, they'll say it is 1/3 from the tip and 2/3 from the base, right? 1/3 from the tip, 2/3 from the base. But if it's a rectangle, it will be at the middle. That's, we divide the length by 2. Same thing for a trapezium. If it is at the middle, we divide the length by 2. So this is 2 plus 5 plus 2. That's a total of 9. 9 divided by 2 is 4.5. So we have where the point load will act. We can also take it as we are separating it. So you can say this is a UDL here. This is 26 kilonewton. This is another UDL. That's the triangle. This is 26 kilonewton. And this is another UVL. That's what? 26 kilonewton. To calculate the reaction, that is, we can convert this to a point load, and then to a point load. So we'll have 3 different point loads. So for the sake of time and to ease the process in calculating our reaction, we are just going to use everything as a trapezium. So we are just going to say area of a trapezium 1/2 a plus b close bracket height, which is equal to 1/2 into bracket. A is from here to here is 5. This is A. That's 5. Plus B is from here to here. That's 9. Close bracket. Our height is 26. And what do we get? We get 182 kilonewton. Where we want it to act. So let me just draw it here. We have this, a mini diagram. So we have a point load acting on 4.5, 182 kilonewton. We have RAY, RAX, RBY, right? Well, if they said the centroid of the trapezium is 1/2 of the base, that is, the centroid CX will be equal to 1/2 times the length of this, which is 9, which is equal to 4.5. So if from here to here, it's somewhere around here now, it's 4.5. It's 4.5 minus 2. So from here to here will be 2, and from here to here will be 2.5. So this will be 2. This will be what? 2.5. So we're going to take moment about A. I'm sure we all know why, because we have 2 unknowns here. So taking moment about A, we have summation MA is equal to 0. Clockwise moments are positive. So if you are taking moment about here, and this is moving like this in this direction, move in the clockwise direction. So that's 182 times 2.5, right? Then this is moving what? In the anti-clockwise direction. That's minus RBY times 5, which is equal to 0. So let's punch it in on our calculator. 182 times 2.5, which is equal to 455. So minus RBY minus 5RBY is equal to, if this one goes to the other side, it becomes minus 455. Negative will cancel negative. So RBY will be equal to 455 divided by 5 divided by 5, which is equal to 91 kilonewton. Right? I'm sure we understand how we've gotten our reaction. So let's move on to the next part. So we are going to be sectioning this now. So what I want you to take note of is we are going to do it stepwisely, the same way I talked about us separating it. So if we are going to section this part now, sorry, my diagram is not so nice. Vx, mx, from here to here will be x. This is where our first section, right? Then let's do it this way. Our second section, that's taking this triangle into consideration, rectangle rather. Just going to do it like this. Oh, I forgot something. We are sectioning this part. This place has to be there, right? Pay no attention to whatever this is. This is our UDL here, and then this is our UVL. This is our UDL here. This is this from here to here will be what? From here to here will be 2. Here to here will be x. This is now Vx, mx, right? We have, okay, we've not calculated RY. So let's just do it up here. Summation f of y is equal to 0. Upward forces are positive. We had that this one coming down, the total is 182. So minus 182. These two are going up, plus RBY plus RAY. So, and we have that RBY is 91 minus 182 plus 91 is equal to 0, plus RAY is equal to 0. So this minus 82 plus 91 is minus 91 plus RAY. Goes to the other side, it becomes positive. So RAY is equal to 91 kilonewton. So we're just going to put 91 kilonewton here, right? So, and then the third one. So instead of us to, if we come and section it here, we section this part, we section this part. If we section it here, it's going to give us issues with this shape. So we're just going to be taking this part, the end, which is going to be like this, right? This is 26 kilonewton. We don't know length x. So I mentioned that if you are sectioning the other side, our moment has to change. So if this is going in the clockwise direction, this will have to go in the anti-clockwise direction, mx, vx, right? Okay, so let's still start solving. You see how I've divided the shapes. So if you join it together, we all get the same thing that we have here. So looking at this one now, let's convert this one to a point load quickly. This is 26. So this will be 1/2. This is a triangle, base times height times base is x, height is 26. So this is equal to 26x divided by 2, which is equal to 13x, right? So we have that our point load, it will be this point load from here to here is x, right? It will be 13x. So the centroid of a triangle demands that it starts from 1/3 from the base, right? So this will be 1/3 of x. That's from here to here. That's 1/3 of x, right? Then we have our vx. Then we have our mx. So quickly, I'm going to be calculating. I'm just going to be calculating the moment equation. I'm sure the vx equation is not going to be hard for us to calculate. Mx. So take mx about the place that is cut. Our moment, we take it about the place that is cut. So summation of moment about x is equal to 0. Clockwise moments positive. So we have mx minus 13x times. Remember, from here to here, this is going in the anti-clockwise direction. 1/3 of x, right? So mx will be equal to, let's just this is okay. Let's not do it equal to like minus 13x squared over 3. Right, I hope you understand. So mx moving to the other side is equal to 13x squared over 3. When x is equal to 0, it's obvious that mx will be equal to 0. And if you have our x, it's from 0 to 2. That's the maximum length of x. So when x is equal to 0, mx will be equal to what? Mx is going to be equal to 17.3, right? So moving to the next one, what do? We have mx going in the what direction? Clockwise direction. So I'm just going to write out the equation. We have mx minus, remember that this one now is a UDL, this is 26, and we have the length from here, so we are going to convert this to a point load. So let me just do it in this mini triangle here. So this is 1 over 2 times 26 times, we have from here to here 2. So what do we get? 2 cancel 2, 26. And where is it acting? It is acting at 1 over 3 from the base. So that's 26 as a point load moving in this direction, right? So from here is 1 over 3 of 2. So 1 over 3 of 2, 1 over 3 times 2 is equal to 2 over 3, right? So for this point load here to move all the way to this place, right, that's in the anti-clockwise direction, that would be 26, that's the point load, times 2 over 3 plus x. I hope you understand, right? Then we now have minus, this will be 26, remember 26, this UDL will be 26, so area of this is length times breadth, that's 26 times x. And where is it acting? 1 over 2 from of this, that's where the centroid of the triangle is at, minus 26x, right? Length times 1 over 2 of x, right? Is there anything we have not added? Yes, this one moving in the clockwise direction, plus 91 times x, right? So we have mx minus 26x square, that is this one now, 26x square, right? 26x square divided by 2 plus 91x, that is this. So coming to this one now, this should be minus 17.3 minus 26x. 17.3 from 26 times 2 over 3 is 17.3, and 26 times x is 26x. So we'll just quickly arrange it to mx is equal to minus, I don't know if you can see it, minus 13x square plus 91x minus 26x minus 17.3, right? So mx, sorry, this is all equal to 0, equal to 0, equal to 0. So mx moving to the other side, this will be positive 13x raised to power 2, right? Minus 65x, that's 91 minus 26, this will be plus 17.3, right? This is our moment equation. So at m equal to 0, we know that as this point, you're meant to get the last answer we got when we're doing for this side, right? So at m equal to 3, you know that at m equal to 0, this place becomes 0, this place becomes 0, you get 17.3. At m equal to, let's see, x ranges from this to this. At m equal to 2.5, at x equal to 0, mx is equal to 17.3. At m equal to 2.5, mx is equal to, let's quickly punch that in our calculator. So we have 13 into bracket 2.5 close bracket all square minus 65 into bracket 2.5 close bracket plus 17.3. That's we get minus 63.95. So at m equal to 5, that's imputing 5 into all this, that's it from here to here, that's the maximum length from here to here. So at m equal to 5, we get 17.3 kilonewton per meter. That's units for moment. Then for this last part, this will be from here what we calculated at this other side. This will be 13x, and remember that it will be acting, that's the point load is equal to 13x, and it will be acting where 1 over 3 of x, 1 over 3 from the base. So you know that the answer you get for here should be the answer you get here. Okay, all right, let's go now. So we have mx is going in the anti-clockwise direction, so minus mx plus 13x into 1 over 3 of x. This now becomes minus mx plus 13 square over 3. Do you agree with me? So when x is equal to 0, that is here. Okay, mx will now be equal to 13x square over 3. At x is equal to 0, mx will be equal to 0. We all know that because this will multiply this to become 0. So at mx equal to 2, here to here 2. At mx equal to 2, that's 13 into 2 whole square over 3. Mx will be equal to, let's quickly punch that, to 13 into brackets 2 close bracket all square, all divided by 3. 17.3 kilonewton per meter. The same thing we got here. So let's go to our shear force and bending moment diagram. Okay, so this is the beam design app, helps us to draw our shear force and bending moment diagram. So I just went to member, this is a beam, I clicked on beam, I put a specific length, and they're asking me what's the length. I want the length is 9 meters, so I'm just going to click on OK. You see 9 meters here, and then we are going to put our support now. We want a hinge support, we want it somewhere around here. Location, it is on the 2 meter side, right? We click on OK, then we click on the support again. We want a roller support. Where do we want it? We want it somewhere around the end of the beam. Sorry, at what distance? At the 8 meters distance, because remember we had 2 meters, then 5 meters, then another 2 meters. Sorry, that is 7. Okay, so we want to start putting our reaction. We have distributed on this end. They said what is the first size? The first size is starting from 0 and ending at 26, right? At what length? Just 2 meters short. Okay, you've seen it, right? So it has started forming our shear force and bending moment diagram. So we're going to add another one. We want a distributed load from this point to this point. What is the first size? First size is 26. Okay, it is a UDL, not a uniformly varying. For uniformly varying, it is starting from 0 down to 26, but from UDL is uniformly distributed, so it's from 26 to 26. So what is the location? 2 meters. What is the length? The length is 5 meters. Okay, you see, then remaining this end, so we are just going to click on this distributed here. First size is starting from 26 rather. Okay, and it is ending at 0. What is the location? 7. What is the length? 2. Okay, so you can see it now. This is how your shear force and your bending moment diagram will look like. So you have your reactions here and here. We got 91, and then this is your bending moment. You can see it on this side moment. You can see this one shear force. So we can see that it went from here, we got 73 up, then down we got minus 63.93, back up again 73.33 to 0. And then this is for our shear force. So you will see that your shear force, just to check your answers, to be correct. So we can use this as a guide in drawing our shear force and bending moment diagram. Thank you.